Okay, so welcome back to another video. So in today's video we have an infinite sum. The infinite sum from n is equal to 1 to infinity of h sub n divided by 2 to the power n multiplied by n squared. And so keep in mind that h sub n is actually defined as the nth harmonic number. So this is the nth. Our partial sum from k is equal to 1 all the way up to our partial sum n of 1 divided by k. Basically, this notation is basically the sum of all the reciprocals at the nth for the first n natural numbers. So from that, we're basically calculating an infinite sum of a partial sum. So that's like two sums like combined together from there. So from pretty much from here on, we're just gonna there's actually gonna be a lot of like uses of integration. Specifically, we're actually gonna, the first step we're gonna do is we're gonna take a little observation from our of our given series and then rewrite some things from there, and then just jump forward from here. Like I said, there's an observation I want to make. Notice that if I take the integral from 0 to 1 of we'll call this variable y to the power n minus 1 dy, then if I were to integrate this, I get that this is 1 divided by n, and then multiply by y to the power n, and then integrate this from 0 to 1, and so I get that this is just simply just equal to 1 divided by n. And so I'll take another observation that notice that if I were to take, let's see, the integral from 0 to 1/2 of, we'll call this variable x to the power n minus 1 dx, then if I take its antiderivative, and well then the definite integral, then I get, let's see, same thing, 1 to the divided by n, x to the power n from 0 to 1/2, and then if I integrate this, or rather not, well already it's already integrated, but if I were to plug in the bounds, I'll get that this is 1 over n, and then plug into here, so this is 1/2 to the power n. So therefore I get that this is just 1 divided by 2 to the power n, and then multiplied by n. So then what this implies is that 1 divided by 2 to the power n squared is simply a product of these integrals over here, 0, 1, yn minus 1 dx or dy, and then multiply with the integral from 1/2 xn minus 1 dx. And so really this actually converts into a double integral. So this means that this so I'll call our given s is equal to this infinite harmonic series, n is equal to 1 of h sub n, then divided by 2 to the power n, and then n squared. Simply when we rewrite all this, I'll get that this is the infinite sum, n equals 1. I'll put the hn out here, and then combine with our two integrals, the product of two integrals. So let's see, y n minus 1 dy, and then the integral 0, 1/2 xn minus 1 dx. And then that actually converts into a double integral. That means h sub n, and then the integral from 0 to 1, and then 0 to 1/2. So basically, this is actually just, since we're combining products, it's basically just using Fubini's theorem. So x to the n minus 1, then y to the n minus 1. And we're integrating this first with respect to dx, dy. And then they both share the same exponent, so what I'll do is, let me fix this little exponent over here, and probably over here too. So that means I can actually combine this into the same base with the exponent n minus 1. Then, okay, so infinite sum 1 h sub n, then the integral from 0 to 1, 1/2 of x times y to the power n minus 1 dx dy. And so now what I want to do here is that let's just focus on our let's not worry about the sum notation, let's just focus on the inside of this integration. So I'll move the h sub n into our inside of our double integral, and then we have a x to the y to the power n minus 1, so with the negative 1 I'll just put that under the denominator. Excuse me, I take that back about saying leaving the series on the side. We're bringing our infinite sum into our double integral. I have no idea why I said that from the beginning. 1 divided by x times y, okay, and then now times the infinite sum, n is equal to 1, then h sub n, then multiply with x times y to the power n, then dx dy. That's what we established here. So I'm just gonna underline this in black for now. And so now the next thing I want to recall is that the generating function of the harmonic numbers is actually defined as the following. So we have the infinite sum, n is equal to 1, and then h sub n to the power, or times x to the power n. That's simply defined as the negative natural log of 1 minus x, and then all this being divided by 1 minus x. Using this little fact here, so that means I can actually rewrite this using replacing the h sub n with the negative, well, the series with associated with h sub n, and replace this with this function over here, the negative natural log. So then when I do this, okay, let me just rewrite the what we have over here. So let's see, 0, 1, 0, 1 half. So let's see, 1x times y, then the infinite sum, h sub n, then times y n, dx dy, and then just replace our generating function from over here. So that means we get that this is the negative double integral, and then this is the natural log of 1 minus x. Specifically, we're dealing with xy, so this will be the natural log of 1 minus xy, and multiply with xy from over here, so xy, and then 1 minus xy, and then dx dy. I'm actually just gonna draw this little arrow over here just to move on to the next step. And so what I can do from here is I can actually, using partial fraction decomposition, I'm just gonna skip that work, and then if you want to decompose this yourself just to verify the following, then you're feel free to. But skipping all that step, using partial fraction decomposition, we get that this is the negative double integral. Let's see, so same bounds, of course. This is the natural log of 1 minus x times y, then divided by xy, dx dy, and then subtract that with the double integral. Same thing from 4, except we're gonna actually this time end up with a different denominator. So let's see, 1 minus xy, then divided by 1 minus xy, and then dx dy. Let's actually first, we have to evaluate these two double integrals over here, but let's actually start one by one and first evaluate this double integral over here. Now, moving from over here, so let's see, double integral 0, 1, 0, and 1 half. ln, just ignore the negative for now. We'll come back to that later, but let's just focus on just this itself. xy, then 1 minus xy, dx, dy. Now, what I'm actually going to do here is that I'm actually using Fubini's theorem and actually switch our bounds of integration. So really, this here is supposed to be, so what we're integrating first is, so this is 1 half, this is 1. And then, but that also means that I have to switch our differentials over here. So that means we're differentiating this first with dy and then dx. Doing this will actually make integration a lot easier. So how to do this? Well, simply just take the u substitution. So I'll let u equals the natural log of 1 minus xy, then du is equal to 1 divided by 1 minus xy, and then take the derivative of the inside, but that has to be in respect to y. So that means we'll end up with a negative x dy. Okay, and so now what that implies is I'm gonna actually just divide negative x to both sides. So I've got negative 1x. I'll move that outside the integral since this integral depends on y, but now we're depending this on u as well, so x is the constant. So then this will just be u du. So the ln of 1 minus u, that will just cancel from the, that will replace that with u, and replacing our du, that will cancel the denominator from here. So then we have that this is negative 1x, and then multiply with 1 half, and then ln of ln squared specifically of 1 minus xy. And then now moving this forward, then we get the new integral from 0 to 1/2, and then evaluate with our bounds. So let's see, this is negative ln squared 1 minus xy, and then I divide this with 2x, taking it with our integration bound between 0 to 1, and then dx. Now I'll just factor out the negative 1/2 outside, and we get 0, 1/2. So when I actually evaluate this, when I plug 1 for y, this will just be 1 minus x, so that'll be fine. If I plug 0 over here, this will be 0, then ln of 1 is just 0, so the whole thing just becomes 0. So really, we have just negative 1/2, because I just factored that out simply. And then this is the natural log square of 1 minus x, and then divided by x dx. So now that's the last thing to calculate. And there's a special value to this. I'm actually not gonna show the work for this, but you can actually verify this yourself if you want to. There's a bunch of special values that are actually gonna come up in this video. I'm just gonna put a little disclaimer. I'm not gonna evaluate those special values simply because there's other resources out there that you can actually look up for that. So we're not really here to solve those special values. We're here to evaluate this. So we're basically just taking the jumps from there. So it's negative 1/2, and then evaluating this definite integral, we get that the following is that this is 1/4 multiplied with the Riemann zeta of 3, and I subtract this as 1/3 ln squared of 2. And then now that means, now if I just distribute, so I get that this is negative 1/8, then the Riemann zeta of 3, and over here this will be plus 1/6 ln squared of 2, or actually I think this is supposed to be a ln cube. Right? Yeah, cube. This is supposed to be a cube. This is our term that associates from where is it? From over here specifically. So just like drawing contour integration, when you're sketching out your contours, you actually define a line. How about I actually just draw the arrow to help specify where is this in relation with. Now the next thing, now that we solved that, now we had to actually solve for our other integral. So ln of 1 minus x, and then divided by xy, that double integral, you know. Okay. Notice that I'll put this little fact here in black as well. So we know that since the natural log of 1 minus xy is actually just equal to the negative infinite sum of, let's see, this is just xy to the power n, and then divided by n. And this is for all, the absolute value of x is less than 1, and then the absolute value of y is less than 1. Then, using this fact, we can actually replace our ln of 1 minus x for this this series over here, the Taylor series. Now this will become, well, just to rewrite the double integral 0, 1, and 0, 1/2 of ln of 1 minus xy, then divided by xy dx dy, simply just equal to the same double integral. And there's a negative over here, so let's see, negative, and then 1/xy, and then multiply with this with our infinite sum, n is equal to 1, then xy n, and then divided by n, then dx dy. And now, so I'll actually just drag the summation outside of our double integral, and the same thing with the n. And then skipping another thing to notice that we have a 1/x times y, and then there's the same base over here, so I can actually rewrite the exponent. So let me slow down things a little bit. So this is the negative infinite sum, n is equal to 1/n, and then with our double integral 0, 1, 0, 1/2 of, so this is x times y, and then to the power n minus 1 dx dy. Notice that we go back from our earlier double integral from, where is it? Right here. And we said that that was actually equal to 1 over 2 to the power n times n squared. So simply replace this double integral with this value over here, and then just multiply with the 1 over n. So you'll get that this is just negative infinite sum. N is equal to 1. Multiply the 1 over n into over here. So we get that this is just 1 divided by 2 to the power n multiplied by 2 to the power, or n to the power cube. And then from over here, we wanted to now notice that there's actually a little special definition known as the trilogarithm. And there's a formula defined for that, and that says that the trilogarithm of x, let's see, right here is good, yeah. The trilogarithm of x, so Li is equal to the infinite sum, let's see, n is equal to 1 of x to the power n, and then divided by n cubed. Therefore, using that definition, we can say that the negative infinite sum of, 1 divided by 2n, then n cubed, is just equal to the negative trilogarithm of 1/2. That's actually basically our evaluated double integral from here. Now the next thing to notice is that there's actually a special value for evaluating the trilogarithm at 1/2. And so what that says is this is just the trilogarithm of 3 of 1/2. So let's see, so that's actually, the special value is equal to I'm talking about the inside parentheses is going to be this expression, and then the negatives outside that. So this is actually, the special value is 7 over 8 multiplied by the Riemann zeta of 3, and then add that with 1 over 6 ln cube of 2, and then subtract that with pi squared divided by 12 ln of 2. So basically now, this double integral over here is just going to equal to negative 7 over 8 Riemann zeta 3, then minus 1 over 6 ln cube of 2, and then plus pi squared divided by 12 ln of 2. So now we have our two double integrals evaluated. So now the next thing is just to put all the pieces together. So now let's reiterate. So let's see, double integral 0, 1, and 0, 1/2 of, let's see, the natural log 1 minus xy, and xy dx dy, and then I subtract that with the same double integral, except that we have a different denominator. Let's see, ln 1 minus xy, then divided by 1 minus xy dx dy. Now I'll substitute the negative. So this is negative times this whole thing, so that means we're gonna get back, this is 7 over 8 Riemann zeta 3, then plus 1 over 6 ln cube of 2, and then minus pi squared divided by 12 ln of 2. Okay, and then subtract that with this, subtract that with the double integral from over here, so then this is minus, so then I'll add a plus 1 over 8 Riemann zeta 3, and then now subtract that with 1 over 6 ln cube of 2. Now, before I get to the next final step, now you'll see that we combine all our terms together. You see that this term cancels, and this term cancels, and then we can actually add these two back, so then it just gets, not really gets rid of it, but it just knows that they share the same terms. That's why I cross it out, so at least we know like what associates with what. So that means we add these two, so we get that this is just the Riemann zeta of 3, and then subtract that with pi squared divided by 12, then ln of 2. And there we have it. That's our final answer. Therefore, in conclusion, the infinite sum of the harmonic numbers of divided by 2 to the power n of n times n squared is just equal to the Riemann zeta at 3. Subtract that with pi squared divided by 12, and then multiply by ln of 2, like so. Alright then, that's pretty cool if you ask me.